All right. You just got it now?
I'm still like this.
There's no delayed delivery with UDP. Okay, so this next homework. Actually, before we talk about that one, how did the last homework go?
Good.
Good? Everyone got full points?
I don't know. I just.
Yeah.
But it worked.
Within 5
All the
seconds.
elevators got
So,
got
but I
delivered.
was like, okay, I toss out all the global locks and now it runs, and I'm like, this shouldn't be right.
Well, I don't think I have a global lock in my solution. But anyway, we'll look at my solution a little bit too, and then we can discuss differences. So this is homework 9. Now we're using semaphores, and we're trying to implement a few different controllers. 2 of them, one is quite basic solution. You should be able to get that one. Reuse of the barrier, that's sort of a component that you would use in lots of other programs. So that's I suppose that's a primitive that we're implementing. But then our other workers here are a little different. So,
And by the way, the test just passes
Yeah.
even if you don't do anything.
I was looking at the .c file and it doesn't really look like it's doing anything. It just prints out the pass
the .c, which one?
for worker 1.
Pass. It just always prints out
Yeah,
pass.
it just it doesn't. Yeah.
There is no
it doesn't-
condition on it.
Yeah. And it
It
doesn't.
creates these threads, it runs these empty functions, but then it just.
And then it just passes. And then worker 2 actually seg faults.
Huh.
Doesn't cycle for me.
Seg faults for me.
Yeah, so they're not supposed to do anything, but they're not supposed to seg fault either. That seems a little extreme. Okay, so what do we do here? Why don't we take a look at worker1.c, see what's in there. I don't understand what you mean by this pass, but maybe because I've been doing other things lately. Let's see. Let's work 9. Oh.
All these goddamn seminars, every single time,
See, that's
it's
a
like,
flaw.
I can't get Oh shit.
Okay. So this one doesn't do much. I don't know what the pass part would be. Let's take a look at worker1 test.c. Maybe that explains what's going on. Let's see. So you're saying it's printing out pass, or?
Yeah.
Yeah, it
Prints out pass.
go a little bit down where it's just a print statement.
It doesn't do anything.
Yeah.
Huh.
And it's
Oh.
It's supposed to check for something. It never checks any variables.
Yeah, that seems like a poor test case. So it passes both of them?
All 3.
Interesting. So I'm just checking that they actually finish. I'm checking for deadlocks, but I'm not checking for functionality. Okay. So I'll have to improve this worker1 test slightly.
Now, what does it have to?
So these guys are supposed to... yeah, I suppose I'll have to even add something. Let's see. Wait for service.
What request? What service?
What's the correlation?
Yeah, okay, so we're going to have to add a couple of function calls there that they make when they are ready to go. And then I'll check that they actually show up in the right order. Let's see. Yeah, so what we'll do is there'll be a function call for the worker, I suppose. Let's see. Yeah, so the worker will have to write something like call work when it's ready to work. And then it should only call work when there's actually a request ready for it to be worked on. That's so there'll be Okay. Maybe I should change that now. Let's see. No, that's not a good idea. All right. So for worker 1, we'll have an extra function call, and the worker just supposed to call work at the right time. So the right time is whenever there's a request has come in. So if we look at the browsers, let's see here. We can't look at the browsers. Yeah. Okay. So browsers call wait for service. Right. So there are all these browser threads. Maybe I should switch to 2-panel here. All these browser threads. See, all they do is a number of times they call wait for service, and then this randomize. It waits for a little while. Sometimes it yields the thread to the CPU. It just kind of makes things not really occur in the same order all the time. Okay, so the browsers wait for service, and the workers, they wait for request. And the whole goal here is you want to be calling, see here, wait for request. Actually, we don't even have to do this, do we? You don't have to change anything. I just have to print something here. So if I say I go like that, oh, and I put another one over here, worker. Now we would want the outputs to be worker browser, worker browser, worker browser, worker browser. That's all.
So this web server part is just like not really web server, it's just...
Yeah, there's no real web server in here now. But a real web server would have the same problem. Right? You have all these worker threads, and they need to know when something's going to happen. We wanted to keep this a little small because otherwise there's so much other code to worry about. But maybe it's a little too small. It's hard to sort of get the concept. Okay, so I'll take a look at it. Maybe I can make it a little bit more fleshed out to make it a little clearer what's going on. The next one should be a little more obvious. So for worker 2, there's 2 kinds of threads, and they all call. So you have some worker threads, but every request requires a couple of threads, a couple of workers to complete the request. So maybe the scenario might be, oh, this is a pretty big request. We need to use more than one core so that it goes quickly. And so now you need to coordinate 2 cores running at the same time. So we have, there's actually 3 threads happening here. There's one being the front part, front end, and we have 2 back ends, and we want them to end up in groups. So you have a front end and 2 back end threads together, and then another front end and 2 back end threads together, like that. So the same thing is going to happen here. Now, when they call group, if we look at this, the code for this, same thing. Worker 2 doesn't do anything. For some reason, my machine is very, very tired. So here we're calling group just arbitrarily. Whenever the backend is ready for another service, we call group. So that, what's that going to do? If you just look at the test, how that works. It basically prints out. No, we don't print it anymore. But it checks. Oh, what kind is this? Is this worker? So now, if we have, at some point, we end up with 2 workers and 1 front end. Then we're good. Okay, so we let those out. We start over. So you see here, we're checking. Okay, so 2 back ends, 1 front end. Then we're good to start over. Otherwise, if there's more backends than 2, or if there's more front ends than 1, okay, now we have a problem. let's see what's going on over here. Oh yeah, so this is a little special case here. If your code is weird, you might end up calling with the same backend thread. You might call group and then exit, and then you call group again. And so now you have the same backend thread represented twice in this group, and that's just not correct. Okay, so we're making sure you want to have two threads, two back type threads and one front type thread in any one of these groups. Is that one a little more clear?
And like the back end threads will be calling back ready and the front ends will be calling front ready?
Yes, exactly. So why don't we try running this one? Let's see. Crap. Let me first see why my machine is so crazy slow.
Let's say we already implement a barrier, so can we just include the .h for the barrier and just use it?
Yeah, that's fine if you'd like. Now barrier is going to be a little difficult. Because barriers, they don't know anything about the type. So now if you set a barrier for 3, let's say, you might get 3 backends and no front end. Probably a barrier is not going to be helpful for this case, but maybe you can work out something. Let's try this out. So you said this one seg faults. Oh, worker 2 seg faults. Yeah. Okay. So this is clearly not the answer we want for the worker 1. Right. Now we have workers and browsers, and they're just happening in any arbitrary order. We want them to be paired up. So basically, first a worker, then a browser, and then so on. Let's try worker 2 test. Yeah. Okay. So this one's very upset because it got 3 backend threads and got no front-end threads in the first example here. So let's just see what happens here. If I print something out over here. Huh? Oh, print, great. Right. So here we got 3 calls from back ready. Right. So 3 of these backend threads were ready, and they'll just call group right away. So what we need is some sort of synchronization over here, so that 2 of them go for it, and then we have to wait for the front to come in. So again, we're doing this just with semaphores. I don't know if it would be helpful to have the other any other operations. Probably not particularly. So semaphore is actually a pretty good primitive for this problem. And I decided we'll add another bonus piece. So 5 bonus points for one more problem. I haven't put up the definition yet. And we'll probably add a week too. We have 2 homeworks to go, and we have 3 weeks, I think. So I think we'll add another week. Either way, so the final problem is now we have readers and writers, front ends, back ends, whatever. Actually, reader-writer probably makes more sense. And they're coming in at both coming in at a high rate. But it's a kind of a new storage device that we're using. The storage device allows any number of readers at the same time, any number of writers at the same time, but you can't have readers and writers concurrently. And it takes a while to switch between the 2 modes, reading and writing. So what we want is basically, if you have a whole bunch of writers, like we want to put them all together, do their writing together, and then switch over to reading, because now probably you accumulated a lot of readers, switch over to doing reading, and then back. Right? So keep doing back and forth like this.
So there can be multiple writers at the same time?
Yes. So this is a strange storage device that allows lots of concurrent writers. There's no limit on the number of riders, at least in the current setup. But yeah. So we'll probably talk more about that one later because it's a kind of a tricky. It's considerably harder than what's in the current homework, I would say. Yeah.
And just one more question, because in lab we were to set up the semaphores. Like we were trying to use the sem open in the beginning, but then we just switched to sem init. Is that fine?
That'll be fine. It's gonna be a problem on if you want to run it on a Mac because sem init doesn't exist anymore there. But if you have sem init in the Linux version on Amazon, then that's fine. Couldn't get it to work.
Yeah. I don't know what else to do. It seemed like great big, right? But I forgot what the error was. Remember?
No file.
Yeah.
It couldn't create the text or the semaphore.
I think I know what it is. You need to start the semaphore name with a slash. Did you?
How would you supposed to know that?
It says in the man page.
That's it.
But it's kind of a stupid, I don't know. So for some reason, I think what happened here was Tim was probably looking at my solution. I built it on the Mac, and I haven't actually tried it on Linux yet. And on the Mac, you don't need the slash. Anyway, either should be fine. There's no big difference between these semaphores, so I wouldn't worry about it. I guess one, let's see. Yeah, so the problem with init semaphores is that you can't use them across processes very well. If you have shared memory between the processes, it's fine. Like a semaphore that you initialize, it sits in shared memory somewhere, right? You initialize it there. But say I start a new program now, and it wants to get in on this semaphore. How would you do that?
There is a flag to share between processes.
Yeah, but how does it find it?
I mean, the flag can be the number. I don't know. It's probably not.
Yeah, so you need some way of referring to the semaphore. So there's two ways, actually. You could have a shared memory segment that is in a file. You mmap that file into every process that you want to work with, and then you know where in that shared memory segment the semaphore is. So you just refer to that memory location. That works. But a much easier way is to use sem open, because then you just specify a name. So every process that wants to use this semaphore, they just open that name, and they all get the same semaphore. It's not like it's a bunch of different ones. So probably I would switch over to using sem open just because it's a good thing to know. But it's not going to affect your solution, I think. Okay. So I was going to spend a little bit, let's see here. Yeah, I'll spend a little bit of time on the homework, the previous homework solution, because I thought we got to get this, make sure we get it right. Make sure we understand what's going on. So I have a whole bunch of different solutions, but it's so sluggish, I don't get it. Top doesn't say anything's running on my machine. It doesn't care, but it's still really slow. Let's see, homework 5. So I'm just looking at the. We used this in 385 before, and I haven't moved over the solution. But other than that, it's the same. So let's see what happened here. Random lift. It's going crazy, this thing. Look at it blinking. Okay. What the hell is going on? I think Emacs really doesn't like the fact that it had Windows on both screens here. Okay. There we go. What is this? Worker test. That's not it. random lift. Okay, so I tried a couple of different solutions, but the one that worked out the simplest was this, where you assign a random lift to each passenger, and then use a couple of barriers. So if we have time, maybe we'll try to make another solution that is a little better. So, but let's see how this one works first. So I don't actually keep track of the passengers at all. There's no need. We just have some state for the elevators. There's a lock deciding who gets to control the elevator. So the passengers are actually in control of these elevators, but only one passenger at a time. And then a barrier for coordinating opening and closing the door. And this here is so that the passenger can tell the elevator what to do. Or this one is, at least. These two are for internal state keeping in the elevator. And so is this. Okay, so we just initialized, nothing special there. The barrier is of size 2 because it's the elevator and the passenger that need to coordinate, so it's one each. So let's take a look at the passengers. So actually I should probably stand over here because otherwise the mic doesn't work. So the very first thing is the passenger on a given request decides which elevator to pick. Pick one at random. So we're not sticking with one elevator for the whole duration of the passenger. It doesn't matter, actually. And then right away we grab a lock for the elevator. So now what's going to happen here is only one passenger at a time gets to control this elevator. So it's not like in a small critical section like we would do usually with mutual exclusion, like you try to keep it short and then you exit. Here we're just saying this is my elevator, right? And I'm going to keep it until I've been served and exited the elevator, and then I'll return the lock. So that works out nicely because then the passengers and the other passengers, they're just going to wait politely behind this lock. So now, after that, it's a relatively simple problem. We have to tell the elevator where to go, right? It's my elevator now. The only way that I can get the elevator is if no one else is using it, so I get to tell it what to do. I'll tell it here where to go, right? And then I'll wait for the elevator to come to my place and open the door. Okay? And then I get in the elevator, I tell the elevator where to go, and I wait for it to open, to close the door. Alright, that's actually, I'm not really waiting for that. It's really the elevator waiting for me to be inside. Right? So here we're waiting for the elevator to open the door. I do some stuff. And then the elevator is now waiting for me to be done with my stuff. Right? Telling it where to go. So now I wait for the barrier again. Probably the elevator is already waiting for me. Now we move on. And now the elevator is just moving to the next floor. I told it where to go. I'm waiting for it to open the door so I can get out. And then I leave, and I just, this probably isn't necessary. Just tell it no one's using it at the moment. And then the elevator is waiting for me to get out of the door. So now I wait for the barrier again so that we're clear. Now we're done. So I'm delivered to the other end, and now I can leave simultaneously. Did anyone do it this way? 4 barriers? Okay, cool.
You have 4 different barriers?
Oh, 1 barrier, but 4 barrier calls in the passenger. Yeah.
That concept of keeping track of the passengers. And then the elevator would have one carrying the passenger.
Oh, I see. You had 2 different barriers. One for, or
No, a
no?
lock and then a barrier for each elevator.
Yeah, exactly. Yeah, same thing here.
Yeah, I had 2 barriers just.
Wait, you have only 1 lock
Well, 1 lock per elevator.
per elevator. Yeah, that makes sense.
I had 2 barriers per elevator just to make clear that one was for arrival and one was for, as in get on and push out.
Right. Yeah, it doesn't make a difference because we're only using them separately. So then this code, the rest is not very different from the previous, from the template. I guess there's a couple of nice things there. You don't have to stop at every floor anymore because we know where we're going. That's good. So these are just moving the elevator up and down. And then there's the final coordinating with the passenger bit. So we open the door, we let the passenger in. We wait for the passenger to be done, and that's it. So this solution was actually a line or two longer than the template, I think, but probably mostly because there's a lot of space in there. Okay, so there's a couple of drawbacks to this solution. I suppose the main thing is it doesn't, we don't produce a very good schedule. There's two problems with the schedule. First, I'm picking a random elevator. What if that elevator is busy? And there's some other elevator that's free. This doesn't make much sense. And there's one more problem. Any ideas?
There might be an elevator that's better off going to. There might be an elevator that's closer to you than the one that you're taking.
Yeah, or if you look at it the other way around.
We don't do it in order.
We don't do it in, yeah, okay, so that's true. From a fairness point of view, it'd be nice to do it in order. Whoever clicked first gets the elevator first. If you want the highest throughput, yeah.
The elevator's might not be looking for the closest passenger.
Exactly. If you want to maximize the throughput here, the elevator should really be picking up some passenger that's really nearby. You could even imagine doing better than that. It's a little bit like a game of chess. Like you look a few turns down the road, and you see, okay, if I want to just make the maximum number of passengers happy, I should probably choose the shortest trips too, right? And trips that are nearby, so I can always pick another one. Right? So you can do better, but then of course you'll have some passengers. Whoever wanted to go from the bottom to the top will never get served because it's just not worth it. So yeah, it depends. But I think one interesting addition to this solution would be to look at all the passengers and find the one that's closest for any given elevator. Yeah.
This is in a different scenario. How would you get the elevators to talk to each other so you can actually produce some artificial intelligence with it? Four elevators can figure out what's the most optimal path to go along.
Elevator array. Is any time that they report, hey, I'm an elevator, it's starting with an elevator. That.
Let's see. So you just want all the elevators to coordinate, saying, oh, it's, you know, this one's good for me, but it's even better for you. Maybe you should take it. That sort of thing, or
That's what
yeah.
I feel like if you look at the load that's currently there and try to map out the form to evolve.
Right.
So
So-
track of which floor each elevator is on.
Yeah, optimize the path.
And also all the passengers. So I at least don't keep track of the passengers at all here. So we don't know what requests are in there. They're just sitting behind this lock. So it'll be very hard for the elevators to make any predictions. So I guess the first thing they have to do is forget this global lock, or at least, yeah, forget the global lock. That just doesn't work anymore. So throw it out, and now we have to have all the passengers register their intent in an internal data structure here, and then they have to, the elevators would have to, whenever they're free, look through that list of passengers and find whatever's the best. So now, okay, if you're choosing whatever's best for you, that might be greedy. I'm not sure. Yes, right. So you could imagine, oh, the one that's best for me is like 5 floors away. But it's only 1 floor away from this other elevator who's about to be ready. So they should really serve it, not me. So I think if you want to have, you call it core communication between the threads, but you don't really need that. Just slap a global lock on the
Control units.
yeah, you have some sort of a central control unit. So you say, whenever you want to look at all the passengers and all the elevators, you have to have this global lock, right? And we run some code that looks for all the elevators, which, well, like knowing the state of all the current elevators, which is the best one for this one elevator. Right? So it's not like the elevators have to make an individual decision. They can make a globally optimal decision because all the elevators run the same code.
And then you
That
don't
would be
really need
interesting.
to keep track of all the passengers, but you really need to keep track of the floors and how many people are there.
That's true. Would it help? I don't know. Oh no, you need to know where they're going to, huh? Maybe. Depends on what you're planning to do, right? If you just want to serve passengers and you don't care where they're going, then it doesn't matter. But you still need to know who they are. Because otherwise you can't tell them that, oh, now it's your turn.
Well, the elevator can have a carrying passenger thing.
Yeah.
Then, some of the decisions we... Oh no, never mind. Yeah.
There's something for the coordination there. So you can imagine having maybe a lock on a barrier on every floor instead, or a barrier wouldn't work. So I think condition variables might be something we want to look at for that. And let's see. Is this the time to do it? Make sure I'm not... Well, okay, so I promised that we would finish up the reader-writer problem first. So let's do that, I think. If we're done with this, yeah, I don't think we'll have time to do an improved solution that optimizes. So we'll skip that, at least for now. Maybe we'll do it some other time if people are interested. But let's do a vote. Like on Friday, should we talk about making a really clever solution to this?
As much as I'm
Okay.
interested, I think it would be investment. So.
Well, depends. So okay, so I'll give it some thought. If I can come up with an interesting lecture out of it, then we'll do that. Okay. And then we'll certainly use condition variables, which is anyway the next topic here. But okay, so let's switch tracks a little bit. The problem we left off before must have been last Wednesday, was this readers writers problem. So this is again a semaphore problem. We have a device that allows a single writer, maybe not a device, it's just memory. If you want to write to shared memory, you better not have other people writing to the same variable. You're probably going at the same time. You're probably going to run into trouble. You also probably don't want anyone to be reading while you're writing to it, at least unless it's a single word, which is atomic. So we want to be able to say any number of readers are allowed into this critical section, but only a single writer. And if there's a writer, no readers. So now how do we implement this with semaphores? Because a semaphore, well, again, they don't know about the types, right? So we need to do something a little bit clever. So I think one good solution might be to keep a count of readers, right? And I don't think we need a writer count because there's either 1 or there's 0. So we can probably stick with just a lock for that. In fact, why don't we start with for the writer side? What does the writer do? Let's see. So we need a semaphore.
Reader count would be a bad solution because let's say we have 10 readers and we wait for some predetermined number of readers. But for the longest time, only just one reader wants to read. So it'd be better to have it by type.
Oh, okay. So maybe a little misunderstanding here in the problem setting. The idea is you have some reader is already in there, and now another thread wants to also grab the lock or grab this reader-writer lock. If that thread is also a reader, it's allowed in. If it's a writer, it's going to have to wait until there's no more reader in there. Right? So it's a slightly different scenario. So we're not waiting. The readers are not waiting for each other. They're just saying, if there's one there already, I can go, because they're not going to change the data for me.
What if the reader is never done reading, so the writer will never write?
Yes, that's true. That's actually true for mutex as well. If whoever's holding the mutex never lets it go, no one else gets to.
Oh, yeah.
But there's one very interesting subtlety with reader-writer locks, which is very close to this. You could imagine starving the writer. where there's constant churn. There's almost always new threads coming through, but the writer never gets to write.
So you'd have to set up a queue of sorts.
It's a tricky problem to get that quite right. So you could imagine now you have one reader, another reader comes in, first reader is gone. Now a third reader comes in before the second reader has left. Second reader leaves. Fourth reader comes in before the third reader has left, right? So you have a constant stream of readers in there, but the writer just never gets to go. So in that case, I suppose what you could do is you could say, if there's a writer waiting, then the readers don't get to come in anymore. So let's see. Well, let's start with a basic reader-writer lock that has potential starvation, and then maybe we can figure out how to do one that doesn't starve the writer. Okay, so we need to see here. Let's call it. Oh, we can call it mutex. So if it's a mutex, it starts at 1. So what does the writer do? Well, it does mutex.wait, mutex.signal. Right? It's pretty straightforward because, well, if there's a writer in there, we don't want any readers in there. And well, okay. So let's see. Assuming this is the writer, now what do we do with the reader? So, maybe we should call this something else. But it's not really a write lock either, because you could have. But anyway, why don't we do that? That's fine. It also locks out readers. All right, but. Okay, so now we have to have this reader count. The reason I want to have a reader count is that if there's multiple readers in there, we probably want to take some special action when we reach 0 readers. So we have some readers come in, some readers leave, and now the two critical points here is when the first reader comes in and when the last reader leaves. In between there, we don't care. The readers don't have to do much. As long as the reader lock is held. So we're going to have to do this reader count. This is sometimes called a scoreboard pattern for concurrent programs. So the scoreboard being you have a single lock, a mutex that protects a count. It's a scoreboard. Okay, so now what do? We need another mutex. Count mutex. Count lock maybe. Okay, so we know how many there are. Whoa. Okay. The older generation kind of setup here. So now, if this is the first time a reader came in, all right, I'm not stepping on anything here. There's something crackling.
Yeah, that's not safe.
So if this is the first reader, if there's more than one reader already, then we know that the lock is already held, right? But if we're the first one, we're going to have to get this lock. So let's do that. So we'll say, right, lock.wait.
Yeah. Okay, then we do some reading. And then now we want to decrement again. Holy crap. Is that is there a speaker here somewhere?
Sounded like one. It's probably inside.
Oh, in here, yeah. Well, the display was fine this time, right? There was just some...
Time to write another email.
Yeah, I think so.
Trying to kill the teacher.
Okay.
NSA.
Oh, it's the NSA. They don't like all my gossiping. Okay. So if the reader count is 0,
now we can release the write lock.
right. Oh.
Okay, so what happens here? So first time a reader comes in, well, say the writer comes in first. Now the lock is held. Reader comes in, we increase the count to 1, and then we're going to have to wait here until the writer is left. Writer eventually leaves, then we can continue on, do our work. Now we're doing some reading. Another writer comes in. It's going to have to wait over here. That's fine. We continue, do some more reading. Another thread comes in. This time it's a reader. Reader comes in, grabs the lock, like the count lock is released, so that's fine. You can increase it. Yeah, we released the count lock over here.
But if we were in the waiting,
Let's see.
if you start to wait on the write lock, you never release.
So they just wait in the beginning, that's fine. That's what we want. We don't want two people implementing at the same time.
Right.
So, okay, so the scenario here was we are done here doing some reading for a while.
Usually reader-writer locks are used when you have long reading times.
Because then it makes sense. Like you don't want to have mutual exclusion with multiple long readers. You're wasting so much time. It's much better to have them all doing at the same time. Okay, so we have one sitting in there. We have a writer sitting up here waiting for the write lock. But that's fine. Now comes another thread. Another reader comes in here. The count lock is released. We increase it to 2. We don't do anything here, and we just go for it. All right, so now we're not grabbing the writer lock. This thread doesn't need to grab the writer lock because some other reader already has it. First reader is done, leaves. All right, so now grabs the count lock back, decrements it to 1, so it doesn't do anything. Now it doesn't have the.
Now it doesn't release the lock. It just leaves. So it gets a little curious, right? Because now you have one thread grabbing the lock and another thread releasing the lock. But you could think of it maybe as the class of threads own this lock together. Like all the readers own the lock together. Whoever leaves last gets to unlock it. Kind of tricky business. So there's really a lot of tricky business in these semaphores. So I found this wonderful book, and I think you should take a look at it.
How little is it?
Yeah, it makes me enormous.
It is not all that little. But it's free. So it's really excellent actually. On Amazon, the author says, oh yeah, this version is an old draft. If you want the new one, you can always just download it for free on my website. That's pretty good. So I won't be buying it from Amazon. Anyway, so this guy really knows what he's talking about. It goes through all sorts of different problems. So he's complaining that, in a standard operating systems book, which is often where concurrency is dealt with the most, they typically do like 4 standard problems, or 3 standard problems. Reader-writer lock being one of them. Probably this queue that we did before, the first in, first out queue. Is that what we did? I think we did something like that. It's another sort of classic. But it doesn't give you much opportunity to practice just getting synchronization right. It's like, okay, now I know how to do a mutual exclusion with semaphores. But that's not the point here. The point is to be able to do new kinds of synchronization for your particular application. So this book goes through first some basic stuff, and then it starts talking about barriers. Oh, all right. So you probably did quite a bit of the barrier in lab, did you, with Tim?
Yeah.
And in fact, this is also discussed in here. I think there's a pretty good sketch for the barrier. And then there's also these other stuff, or readers, writers in there. There's, oh look, Dining Philosophers. Yeah, there's actually a few different interesting solutions. Dining Philosophers has lots of different solutions you can try. Cigarette smokers, okay, so, yeah. And now it starts getting less, like, this is all just stuff that people made up, like made up recently. It's not the giants of computer science from the 50s that came up with it. It's just some student at some college, right? Okay, take a look at it. So here we have 2 kinds of employees, 2 kinds of people: Linux hackers and Microsoft employees. And you can never leave one alone with 3 of the other kind. So then the book goes through first some hints, and then usually there's an empty page, and then it's got solutions. Sometimes it's non-solutions as well, saying, okay, you probably think you can implement it this way, right? And then it discusses why not. So here's an actual solution for this one. Okay, so it's an excellent book, and I highly suggest that you use it when you're working with this homework. Right? There's probably not the exact same thing that you're looking for, but you'll find, like, if you read this book, you certainly will know enough to be able to solve these problems. And maybe you find something that's close enough that you can adapt it. So that's allowed, for sure. Oh, and we're out of time. Good. So next time, maybe we'll do a... We'll certainly talk about condition variables. Maybe we'll do a solution of the previous homework with condition variables instead, to do something a little more closer to optimal.
Are we in here for good now?
Well, assuming this thing doesn't electrocute me.
Yeah.